I have already shared with you the slides, the PowerPoint slides, where the whole lectures, the today's lecture, the next lecture, and the very next lecture, they are all uploaded on that slides. You can access those slides and read those slides. So today we will be talking about all those reactions, and I will be uh, through voice message I will be telling you all through the various slides. So one by one we will be discussing all those slides, so the topic is the electrophilic aromatic substitution reactions. As you all know that usually the aromatic compounds do not undergo the addition reactions very favorably. uh, Similarly, they do not undergo the nucleophilic substitution reactions. They favorably undergo the electrophilic substitution reactions. So the most favorite type of the reactions that usually the aromatic compounds undergo are the electrophilic aromatic rings. They are typically the benzene ring. They are benzene is rich with the electron, and there is a high density of electrons, so it rather act as a nucleophile. So the first attack upon the nucleophile, as you all know, is by the electrophile. uh, I mean nucleophile go to attack the electrophile, uh, rather than electrophile comes to attack on the nucleophile. The nucleophile electron density moves towards the electron deficient center at the electrophile. Here the substitution takes place where one or more of the hydrogen of the benzene ring is usually replaced with the coming electrophiles, resulting into the substituted aromatic compounds, or substituted benzene compound. Normally, the you know that aromatic character, the usually the the conjugation or the aromaticity is the most stabilizing factor for the benzene ring. So if any reactions that sacrifice the aromaticity of benzene, that reaction will be occurred at a very special condition. Under normal condition, it is not possible for benzene ring to sacrifice the aromaticity. In the uh, electrophilic substitution reactions, usually the benzene ring, after the replacement of the hydrogen with the electrophile, regain the aromaticity. That's why these reactions are the most favorable type of reactions. As you can see on the second slide of the PowerPoint that I have provided you, that question is that why benzene undergoes the substitution reaction instead of example on the slides. You can see that on the slide number 3, uh, you have been given the cyclohexene, right? So if cyclohexene react with the bromine in the CCl4 as a solvent, what would happen? There will be an entire product, 1,2-dibromocyclohexane will be produced. You already know about how all this works, because there is a formation of the cyclic bromonium ion, and then there is a reopening by the attack of the coming bromide ion from the opposite sides and opening that bromonium cyclic ring and resulting into the entire product. This is the addition reaction. Reaction of bromine with the cyclohexene in presence of CCl4 is an example of the addition reaction. But if the same thing happens with benzene ring, the same reagent bromine is provided in presence of FeBr3. So instead of the additive product, we get the substituted product that is called the bromobenzene. And why this happens? The question is that why don't we have that addition product? Because benzene ring doesn't undergo the addition reaction. The reason behind that is that benzene has to sacrifice its aromaticity on undergoing the addition reaction. So that's why benzene is never can never be willing, is never ready to get or the to undergo the you know addition reactions, because that's it. By doing that, benzene has to sacrifice its aromaticity. On the very next slide, slide number 4, you can see that few other example has been given where the aromatic rings have been compared with the non-aromatic rings. The two different type of the reactions happens. What happens to the non-aromatic rings can never be expected to happens to the aromatic rings. You can see the first example where the cyclohexene is going to react with the osmium tetraoxide in presence of the sodium bisulfate. Now the question is that should it produce the is there a cleavage or something? No, it is it is resulting into the diol. So after undergoing the reactions, it is producing the 1,2-diol product. This is a syn addition. Syn addition to the cyclohexene with the osmium tetraoxide in presence of the sodium bisulfite result into the 1,2-dihydroxycyclohexane, and this is a syn addition. But if the same sort of the reagent is provided to the benzene ring instead of the cyclohexene ring, you can see there that there is no reaction at all. Now why this happens? Because benzene ring doesn't undergo the addition reaction. On the same slide, you can see the next example where the cyclohexene is allowed to react with the water in presence of the acid. So this acid hydrolysis of the cyclohexene resulting into the cyclohexanol reagent, that is the acid and water, is provided to the benzene ring, benzene will not react at all. There will be no reaction. The reason again the same, because benzene does not undergo the slide. The last example on the same slide, you can see where the cyclohexene is allowed to react with hydrogen in presence of the Raney nickel at 25 degrees centigrade and at the pressure of 1 atmosphere. It has resulted into the cyclohexane. So the cyclohexene has undergone the hydrogenation reaction. But parallel to this, you can see that the benzene ring, which has been provided with the same sort of the reagent and catalyst, I mean hydrogen and nickel, high temperature and high pressures, it has undergone the cyclohexane as well. Here you can ask that it has undergone the addition reaction. Why I'm saying that it is not undergoing, the benzene is not undergoing the addition reaction? Actually, benzene can undergo the addition reactions, but for that you need to have some very high temperature and a very extraordinary high pressure. So benzene can undergo the addition reaction under a very special condition at a very high temperature and a very high pressure. Normally benzene, as I said, the word favorably, if you are talking in terms of favorable reaction of benzene, so benzene never undergo the addition reaction under the normal conditions, but under special conditions where along with the catalyst you also provide a very high temperature and very high pressures, this could be a factor that allow the benzene ring to undergo the on the very next slide, I mean slide number 5, you can see that the benzene ring has been compared with the 1,3,5,7 cyclooctatetraene. This benzene, you can see benzene ring uh, is not undergoing the addition reaction with the bromine. But on the other side, this 1,3,5,7 cyclooctatetraene in presence is undergoing the addition reaction with the bromine, resulting into the entire product, one entire di substituted dibromo substituted product, uh, acting just like the normal cyclohexene. Uh, why this is happens? Because benzene is the aromatic compound, and this 1,3,5,7 cyclooctatetraene is an anti-aromatic compound. So it's not aromatic, it's rather anti-aromatic compound. So the question is that what is the difference between the aromatic compounds and the anti-aromatic compounds? All the aromatic compounds, obeys the Huckel rule, as well as there are the four postulates that I have already told you about, that every aromatic compound has to obey all those four postulates. The first thing is that they should be cyclic in nature. There will be alternative conjugated system, alternative single and double bond. And the third factor responsible for the compound to be called as aromatic is the planarity. The compound should be planar. And the last thing is that it should follow the 4n plus 2 Huckel rule, 4n plus 2 system. You already know about the 4n plus 2. Where n is the number of carbon atoms, you can put integer. Sorry, it is the where it started from the 0, 1, 2, 3, 4. So 4n plus 2, the minimum carbon ring compound starting with the 2 carbon for the aromatic system. That is the cyclopropane ring with a positive charge in with a single double bond inside the ring. That is the least possible ring compound showing the aromatic character. So that's obey the 4n plus 2 rule. That is 4. If I put 0 value for the n, that will be 4 zeros are 0 plus 2. It means equal to 2. So it means that the very first aromatic compound is possible with the 2 pi electrons. And starting with the 1 and then 4 into 1 plus 2, it means that 6. Benzene is example for that. So all these series which follow this 4n plus 2 and also obeying the other 3 rules, they are possibly aromatic. But on the other side, this compound, the anti-aromatic, are those compounds which follow all the 3 rules, the same 3 postulates that the benzene ring follow. But along with this, it also follow the 4n rule instead of the 4n plus 2 rule. So the only difference between the anti-aromatic and the aromatic is that the rest of the postulates are both common for both of the rings. The only one difference between the anti-aromatic and the aromatic is that aromatic follow the 4n plus 2 rule, while the anti-aromatic just follow the 4n rule. For instance, the very first example is if I put compounds, if I put 0 value for the n, it will be 4 zeros are 0. It means that 0 pi electrons. So the first anti-aromatic start with 0 pi electrons. So is it possible? And the very next, so it means that it means nothing. It means that if we go ahead with the 4 and value 1, it will be like the 1,3 cyclodiene. Is that? So this is the first anti-aromatic compound. And then the 1,3,5,7 cyclooctatetraene, which is showing the 8 pi electrons altogether following the 4n rule, where the value for n would be 2. So 4 into 2 equal to 8. So it means that any compound showing the 8 pi electron could be anti-aromatic, and so is this compound, this 1357 cyclooctatetraene. That's why it's undergo the addition reaction just like the normal the normal alkene does. It's undergoing the addition reaction because there is nothing wrong with this. It's not sacrificing the aromaticity. Now question is that whether the thermodynamics, whatever we are saying about the addition reaction of the normal normal alkenes and those of the aromatic rings, they are how they are different and how they are behaving different. This can be further explained on the thermodynamic basis. You can see the diagram on the slide number 6, where you can clearly it's clearly evident from this figure that the on the y-axis the potential energy is on the increasing order on the y-axis, but on the x-axis these various rings has been given. So you can see that for the cyclohexene, if the addition reaction happens, the energy barrier is very low. But on the other side, you can see that if we are putting another double bond along with this first double bond in conjugation with the first one, then what would happen? There is a little bit increase in the potential energy. So as you know that as the potential energy is increasing, the stability will be yes, you are right, stability will be less. Greater the potential energy, minimum will be the stability of the compound. Minimum the potential energy for the energy barrier for the compound, more will be the stability of the compound. And so is the case. You can see for the for the one single double bond cyclohexene, for the addition reaction to happens, the the very less amount of the energy is required, and then as we are moving ahead with the two double bond in conjugations, now the energy is going up, and for the hydrogenations, and as we if we are putting three double bond in conjugation, that means aromatic, that is the benzene ring, and you can see there in this figure that the energy barrier has been increased up to minus 360 kilojoule per mole, which is the clear indication that this reaction is very difficult to have. Thermodynamic explanation for this concept, that why the mono substituted, the single double bond compounds undergo the addition reaction, while the aromatic compounds does not undergo the aromatic addition reactions. So this was the explanation in terms of the thermodynamics. Now what the resonance concept can explain this concept. We can also explain why this is different for the cyclohexene to behave differently from the aromatic ring in terms of the resonance factor. Resonance factors say that if we are talking about the cyclohexene, you can see that in a cyclohexene means that a single bond existing in a 6-member cyclic ring. So it means that the bond distance, they are variable. The bond distance between the carbons which are bounded to the double bond, it will be short. It is as much as CC bond length is how much? The bond length will be around 1.39 angstrom, is it? And what about the single bond? And the single bond is about 1.54. degree. So all the the bond length between all the 6 carbon in the cyclohexene are not equal. The CC double bond length is different from the C double bond double bonded carbon and the single bonded carbon and the single bond carbon. So there you can see that there is a variation in the bond length in the cyclohexene, and this is the basis where the addition reaction is very easy to be happens in the cyclohexene compared to the benzene ring, where the uh, all the bond length between the carbon and carbon, they are all equals. That's why for the benzene ring it is very difficult to undergo the substitution reaction. This was the resonance explanation for the above on the slide number 9. You can see that the various substituted products has been given. These are the various uh, derivatives of benzene resulting after the electrophilic substitution reactions of benzene. For instance, if the benzene undergo the sulfonation reaction, it result into the benzene sulfonic acid, where the sulfonic group replacing the hydrogen of the benzene ring. Similarly, the nitration reaction of benzene ring result into the nitrobenzene, where the nitro group replaces the hydrogen of the benzene ring. So is the case of the halogenation resulting into the monosubstituted halogen derivatives such as the chlorobenzene, bromobenzene. Similarly, acylation. In the acylation of benzene, the hydrogen replaced with the acyl group, and the alkyl group is going to replace the hydrogen, resulting into the various products such as the toluene, the ethyl benzene, etc. You can, on the slide number 12, you can see that the addition reaction, though it's very difficult for benzene to undergo the addition reaction such as hydrogenation reaction under the normal conditions, but under a very special condition, the benzene ring can undergo the hydrogenation reaction, which is the addition reaction. If we observe, if we analyze this reaction stepwise, you can see that upon the hydrogenation of benzene ring, in the very first instance there will be hydrogenation of a single double bond, right? So this will if the benzene undergo the hydrogenation, the very first step would be the loss of one double bond because of the addition of the hydrogen, and then we will be left with the two isolated double bond after the first hydrogenation step, after the addition of only one molecule of the hydrogen. Now the another molecule of the hydrogen will come, and this reaction will be a little bit more fast because now the aromaticity has lost, and now we have this conjugated double bond. Now one more hydrogen will be added to one more double bond, and now we will be left with the only one double bond, that is the cyclohexene will be resulted. So this second step is a bit faster than the first one, because in the first case we were dealing with the aromatic compound, but in the second case we are not dealing with the aromatic compound because this is a conjugated system though, but it's not aromatic. But now what about the third case where the cyclohexene absorb the third hydrogen molecule to produce the cyclohexane? This step will be the fastest step among all. Why? Because here there is an alkene. Here is cyclohexene which is undergoing the addition reaction. For the cyclohexene, it will be very much easy to undergo the addition reaction to produce the cyclohexane compared to the conjugated system, but not aromatic. And for the conjugated system, it will be much more easier to undergo the addition reaction compared to the aromatic ring. Slide number 13, you can see that the benzene ring in presence of the sodium and ammonia and the solvent ethanol undergoes the Birch reduction, that is called the Birch reduction, where the 1,4-cyclohexadiene is produced from the benzene. In this reaction also you can see that the Birch reduction, that is the free radical type of the reactions. So free radical is not the normal type of the reactions, remember, because free radical type of the reactions can happen even in the benzene. For free radical it's not a problem, but for the normal other reactions, usually benzene ring never prefer to undergo the addition reaction. But here you can see that there is an addition reaction undergone by the benzene ring in presence of the sodium, which is is the free radical initiator, as you all know, and then ammonia, where the hydrogen is coming from the ammonia, and that is usually attached with the benzene ring one by one, and then a diradical is produced. I'm not going to show you the mechanism of this reaction, because I think in the last semester, I don't remember, but hopefully you will be familiar with the reduction steps, mechanism of this Birch reduction. If not, I will provide you this slide as well.